up to now, so we're now at 4.5 in the textbook, electromagnetic radiation. We've already talked a little bit about light. We haven't really specified the fact that light is a form of energy, but it is. And just since the next figure here is James Clerk Maxwell, I want to, and again, what I'm going to show you is not going to be on the exam, but I just wanted to show you, help you appreciate a little bit what Maxwell sort of did for physics. So,
differential equations.
yeah, he used. I mean, we started the chapter with Newton. Mm-hmm. Newton invented calculus, and Maxwell took it a few steps further with differential equations and tied electricity and magnetism together. And again, like I said, it's sort of difficult to see electricity or see magnetism. So each one of these arrows, though, on this diagram, imagine this is like an arrowhead coming at you. That's what that circle with the dot means. It's sort of, an arrowhead coming at you, and the backside is the arrow going away from you, like the feathers, the flights on the tail either. And it's just a circle. So this is just a coil. So imagine you've got a coil, and we've got a bunch of coils all over the room up here, a bunch of coils. But you slice through that, and now you're just looking at the circles. So the electricity, the electrons are flowing towards you here, and then away from you here in this coil. That's how all transformers work. You go out and hear the buzzing transformer, the big green boxes. That's what's inside of these guys. These lines are magnetic lines, and what you'll notice is that no matter where you look, they're perpendicular. So this is coming towards you, and this is sort of going to the right. So now you're going to have to start thinking a little bit three-dimensional, and I'm trying to do it with my fingers here to show that, here's up, down, here's right, left, here's back and forth. So what Maxwell was able to realize is that moving electrons always create a magnetic field that's perpendicular to it. So keep perpendicularity in mind, but also keep mind the fact that we're dealing, simultaneously with circles and with sort of X, Y, and Z. And all of a sudden things start to get a little bit bent, if you will.
Our magnetic atmosphere, kind of north and south pole?
Yeah, it's the same thing. It's the same thing. If you took these magnetic lines and just kept drawing them, they sort of form these infinite donuts or infinite toroids, if you will. So again, this is just kind of fun bonus material. So Maxwell was, sort of grew up a life of privilege. All of his education was paid for, and this is what he came up with. So earlier on, I told you that Newton sort of stole Galileo's two laws: objects in motion stay in motion, forces are equal and opposite. And then he added force equals F equals ma. So what Newton did, he took Gauss's law, which basically says if you add up all of the, actually let's do it down here. We'll look at we'll do the differential things. So if you take the field lines, so in this case E is just, it's just the direction that voltage points. So if we go back to our lecture notes, the voltage itself doesn't have a direction, but obviously if you've got an anode and a cathode, the direction that it flows in some direction. That's exactly what this E is. It's the voltage gradient. So again, high voltage, don't go near the lines. Why not? Because if you get close enough, it's going to arc towards you. So high volt. So there is a direction to that, and that's exactly what this equation is telling us. And if we add all those up, there's some charge inside of it. We can sort of count up all the electrons inside. So that was Gauss's law. It's just electronic counting is all it is. Gauss also said that if we sum up all the magnetic field lines, so B represents, let's get back to the little Wikipedia page. B actually represents all these curvy lines. You know, so it's, again, so B is a vector, just like force and velocity we talked about a little bit. So that's what B is. And so these were well known. It was sort of well known that electrical charge is conserved. That's what Gauss said. It was well known that if you add up all the magnetic field lines, they don't point anywhere. They just sort of, you know, they point in all directions at the same time, but nowhere. And then, so here's Faraday, you know, moving things around with magnets and charges. And so this says, like, as the field changes with time, so as we're sort of waving a magnet around, it produces an electric field in the perpendicular direction. So this little X just means perpendicular, is really all it means. And so no matter which way you look, the magnetic field is always perpendicular to the electric field. So that was relatively well known. Actually, I beg your pardon. Amperes Law was well known. This fourth equation was really Maxwell's contribution to tie these other things together. This one just says that as the magnetic field flows around a wire where electric charge is moving back and forth through it, it's going to be proportional. So the quicker that quicker that electric field changes. So if you think of an AC circuit, for example, and think about the fact when you turn on your microwave, your radio goes haywire. That's all that's saying. So as those electrons are oscillating back and forth in your microwave, something happens to the magnetic field and screws with the other signals. So, and then Maxwell tied all this together. So those four equations sort of are this particular individual's contribution to scientific theory.
I wonder if anyone has written down an equation for the bioelectric magnetic field that humans give off.
Yes.
Yeah?
Yeah. The answer is yes.
Okay.
Because if you look, if you look at the next figure, you'll see that we actually are relying on that all the time. So if you go and do imaging, if you've ever had a CAT scan or an MRI, you're actually firing electromagnetic waves through your body, and that's what you see. So here's your
You can't have anything metal on.
right.
Yeah, because it's magnetic.
Exactly. No ferrous materials inside the MRI, please. Yeah, but here's X-rays at relatively high energy. Here's infrared at relatively low energy. Microwaves, that's your cell phone, and then here's your TV. You get way down here. You've got gamma rays. This little stripe right here, that's what our visible world is composed of. That's what we see. That's what our eyes detect. The next little chunk I want to show you, because Planck is mentioned here, is that E equals h nu. When we did that experiment with summary 1, that little equation with summary 1, this equation is inherent. And in fact, I'm just gonna ask you, let's just do this. This is a good little thing to do in class. I'm gonna give you all the information that you're gonna need to tell me how much energy, we'll just do it in joules. I want you to tell me how many joules are in a green photon. So I've got one green photon. How much energy in joules is in one green photon? So this is Planck's constant. This is the frequency of the photon. So let's just go up and look up the frequency of a green photon. We might even be able to find it on this little scale here. So let's zoom in. Let's zoom in. Maybe, come on. There we go. Whoa, hey. Get this guy under control here. So we've got wavelength on this side, and So let's just remember, on the left we got wavelength, on the right we have frequency. So we'll zoom into green. And we're not going to be 100% accurate, but so this is 10 to the 15th hertz, this is 10 to the 14th hertz, so let's just call that, what do we want to call that? 3 times 10 to the 15th hertz, or maybe, 3/10 of the way up there. So the frequency, so nu equals 3 times 10 to the 15th hertz. This is Planck's constant. Let's go look that up. Planck's constant. This is kind of weird. But it is and it isn't. If you remember, we defined the joule as 1 kilogram times 1 meter squared divided by 1 second squared. The only thing that's missing from this thing is 1 over seconds. So there are the units of Planck's constant. This is actually a joule second, because all we've done is multiply a joule by a second to get those dimensions. So go ahead and write that down. 6.626 times 10 to the negative 34th meters squared times kilograms divided by seconds. Write that down and then convert that into joule seconds and then solve the problem. So 6.626. So H equals 6.626 times 10 to the minus 34th. Okay. Minus 34th kilograms meters squared per second.
Doesn't matter if the meter squared comes from kilograms?
It does not. Meter squared coming before kilograms, just run that through your same algebra machine, because 3 times 2 equals 2 times 3 equals 6. Yeah. So meters squared times kilograms equals kilograms times meter squared. Yeah, that's a fun and handy property of multiplication. Yep. Does not matter. Okay, so I'll just give you a couple minutes to chew on that, and I'll be right back. I'm just going to pause this. Okay. All right, so for those of you listening at home, hopefully you paused your recorder and solve this. Either way, let's just go ahead and look at the solution. So again, we were trying to find the energy of a single green photon. This is Planck's constant, Planck. Really quickly, Max Planck, 1858 to 1947, was a gifted student of both music and physics. He chose the latter as his career and won the Nobel Prize in 1918 for the concepts of energy quanta. The fact that energy is not continuous, it comes in little nuggets or packets, quanta. He was president of the leading German scientific society, but crossed swords with the Nazi governments of the 1930s and eventually resigned in protest at the treatment of Jewish academics. His eldest son was killed at Verdun in 1916, and the second was executed following the 1944 plot against Hitler. In 1945, escaping on foot from the final battles of the war, Planck, aged 87-year-old man, and his wife were robbed and beaten. Found by Americans, they were taken to safety in Gothenburg, where he resumed teaching. So it happened. I took a course from another Nobel laureate at MIT who escaped Nazi Poland on bicycle during the war. And this guy basically demonstrated evolution in bacteria. So it's just amazing what complete idiocracy can lead to. Anyway, so so let's go and knock this problem out. So H, and again, I mentioned this previously, I'm going to reiterate, when you solve these problems, you're really solving three problems at once. There's an arithmetic problem, there's a powers of 10 problem, and there's a units problem. And they're all kind of coming along for the ride. Typically, and this was sort of, you can think of this as elementary school, here's high school, and here's college, right? Okay, so let's just lay them out in one deal though. So we've got 3 times 10 to the 15th, and I'm just going to write this as 1 over seconds. So there's the first part, second part, third part, and we'll multiply that by h. So I'm just going to, for the sake of proving that you don't really need a calculator, and since we just guessed at that 3 anyway, let's turn that 6 into a 7, times 10 to the negative 34th, and then we've got kilograms, meters squared per second. So 1, 2, 3. 3 times 7 is 21. Let's see here. Let's see how good my arithmetic is. Negative 34 plus 15. Well, if that were negative 35, it would be negative 25, but it's negative 19? Okay. Times 10 to the negative 19th times 1 kilogram meters squared over seconds squared. So we just did all three problems. Oh yeah, way to go, way to go.
I did seconds squared, but
Very cool, very cool.
Yeah.
Or we can take away a 10 here and say that's 2 times 10 to the negative 18th joules. So you're basically gonna need 10 to the 18th. You're gonna need 1,000,000 trillion photons just to get to 1 joule. And as we know, 1 joule ain't a whole heck of a lot. It's only enough energy to heat.
How does that just convert to a joule?
Yeah. Well, 1 joule equals 1 kilogram meters squared per second squared.
Really?
Yeah. So
Oh.
it's super handy, super easy.
That's so
If you go all the way back, that apple, remember that apple that weighed, an apple that weighs 100 grams, so equals 0.1 kilograms. If we take that apple and lift it through space by 1 meter, that's a joule, because we're sitting on planet Earth where gravity equals 10 meters per second squared. So that 10 right there in gravity and that 0.1 there in the kilograms equals 1. And there it is.
But is it 1 kilogram meter squared over a second squared? Isn't that the same as just a kilogram meter over a second? Can you just get rid of the squares? Or?
You cannot get rid of the squares. No, because, and this is kind of weird, but they're all 3 different animals.
What does gravity equal?
Gravity equals 10 meters per second squared. So, it's an apples and oranges problem. So
it's just because like meters are squared and seconds are squared.
yeah, I mean, here's a kilogram. I mean, you could tell me how big that kilogram is, but if it's a chunk of black hole, it's pretty small. If it's a chunk of air, it's going to be much larger. But it's a kilogram, it's mass. And then here's your square meter. You know, it's a pillowcase. It's your shirt unfolded. It's the front of your fridge. You know, it's space. I don't know exactly what time squared looks like. I'm not even sure what time just time looks like. But all the second squared, it just means that something is sort of going, and then it's going even faster. You know, 1 second you look at it, the next second it's going faster. Just acceleration.
Yeah.
Okay. So here's your sort of seconds squared, if you want a visual on that. So you can't, like, how do I cancel that one? We could go Einstein, but we're not really going to go Einstein today. Okay. So there's Planck. Just talked about him a little bit. The next section talks about energy proper. Actually, I think this is our second chunk. Let's take one more break, and then we'll wrap it up, so we got a little better packaging on this. I'll talk about the last two sections, which are chemical and nuclear.